So we are back, and if the goal ultimately today is to have a better understanding of things like strings so that we can solve problems with text, let's consider some simpler types of data first, how we might represent those, and then see if that doesn't lead us to a discovery as to like how strings in just today's modern software is using things like that. So when we talked on week 0 about representation of data, we had different ways of doing it in terms of binary and decimal and unary even. When we started talking about the same last week in code, we started talking about data types instead. And these data types were a way of telling the computer, like, do you want an integer? Do you want a character? Do you want a floating point value, like a real number, or even a string, as we've seen? But it turns out that computers, of course, only have finite amounts of resources. Your computer only has a fixed amount of memory or RAM, and that actually has very real-world implications. So for instance, here are some of the data types we've seen thus far. And it turns out that each of these in C has a specific number of bits allocated to it. Now, admittedly, this can vary by system. It's not so much the case nowadays, but for many years, for decades, computers were getting better and better. The earliest computers might have used fewer bits for some of these data types. More modern computers might use more bits. So the numbers you're about to see are pretty much where we are present day. So when it comes to these data types, a bool, which is true or false, somewhat curiously uses a whole byte, even though that's way overkill. Because for a bool, true or false, you of course only need 1 bit. But it turns out, even though it's wasteful to use 8 bits or 1 byte just to represent true or false, it's just easier for computers. So a bool tends to be 1 byte. An int, which we've been using a lot, uses 4 bytes typically, or 32 bits. And if I do some quick math from week 0, with 32 bits, you have 4 billion possible values, roughly. But if you want to represent positive and negative, that means you can represent roughly -2 billion all the way up to +2 billion. So that's the range typically with ints. If that's too few numbers for you, turns out there's things called longs, and longs use 64 bits, which allow you to have like a quintillion number of possibilities, which is a lot, certainly a lot more than 4 billion. So sometimes you might use a long. But even that's finite. And so, as we discussed at the end of last week, bad things can happen if you make certain assumptions as to data because of things like integer overflow or the like, where things wrap around. Then there's a float, which is a real number, something with a decimal point. By convention, it's 4 bytes or 32 bits, which gives you, in short, only a specific amount of precision. It doesn't necessarily dictate how many numbers to the left or to the right. In the aggregate, ultimately, you have, though, 4 billion possible permutations still. If you need more precision for scientific, for medical, for financial applications, you might use 8 bytes, aka a double, which just gives you more digits of precision. They eventually get imprecise per the example we looked at last week, but it at least gets you further down the line. As an aside, in really, really important applications in finance and medicine and military operations and the like, where you really can't have rounding errors, long story short, humans have developed libraries in C and other languages that use more even than 8 bytes. So there are solutions to these problems, but they're always finite. You have to pick an upper bound. Then there's char, which we saw briefly last week when I asked the user for y or n for yes or no. And then there's string, which I'm going to propose as a question mark, because a string totally depends. Like hi, h, I, exclamation point would seem to be 3 bytes. D-A-V-I-D would seem to be 5. So strings clearly are variable based on what you or the human type in. So we'll see what this means, though, in just a bit. This, though, is the thing inside of your Mac, your PC, your phone. Might not look exactly like this, but this is a memory module for a modern computer. And let's go ahead and use this really as just representative of the finite amount of memory that any computer indeed has. Let's zoom in on one of these little black chips on the circuit board here. Zoom in, and let me propose that this rectangle really represents some number of bytes. Like tucked inside of this little black circuit on the board is maybe, I don't know, a gigabyte, a billion bytes, maybe it's 100 bytes, some number of bytes. It totally depends on the computer and how much you paid for the stick of memory. But if there's a finite number of bytes physically implemented somehow digitally inside of this hardware, well, then it stands to reason that we could number those bytes. We can just arbitrarily decide that the top left corner is byte number 1, or really byte number 0. The one next to it is number 1, then number 2, number 3, dot, 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 number 2 billion, or whatever it is, however big this memory is. So if you use a variable in a C program that's only 1 byte, like a char, it might literally be stored in that top left-hand corner of the memory. Like in practice, you don't care where physically it is. But really, the artist's rendition would be this. A char might use one of those single bytes somewhere in the computer's memory. If you use an int, which is 4 bytes, it would give you 4 bytes, contiguous, that is, left to right, top to bottom, but all 32 bits would be next to each other. So the computer knows that those indeed all belong to the same int. If you need a long, or a double for that matter, then you might use a full 8 bytes in this case. And you just keep using and using this memory, kind of like a canvas, almost in Photoshop or a spreadsheet, where you can just move pixels or you can move data around. That's really what your computer's memory is, a canvas for storing information in units of bytes or 8 bits. Now, we don't need to keep looking at these circuit boards. We can abstract it away, as we often do. And let's go ahead and zoom in on this grid just to consider some very specific variables. So let me zoom in. And now I see fewer but larger boxes on the screen, each of which, again, represents a byte. And now let me propose that we play with some actual code. So here in C, albeit without a full program, are 3 ints, score 1, score 2, score 3. I have coincidentally given myself two scores at around 72 and 73, and then a pretty low score at 33. Of course, last week or 2 weeks ago, this would have been high, but now we're dealing with actual integers. So these are 3 so-so scores on my quizzes or tests or the like. So let me go to VS Code here, and let's make a program called scores.c. So I'm going to write code scores.c. That's going to give me my new file. And let me go ahead and implement something like this. Include standard io.h, int main void, and then inside of here, let me do int score 1 will be 72, int score 2 will be 73, and int score 3 will be 33. And then let me just do something like write a program to average my 3 test scores together, something like that. So let me do printf, quote unquote, my average is, and I'm going to go ahead and do, say, %i \n. And now let me plug in the results. And this is kind of grade school math now. How do I compute the average of 3 values? Well, just like on paper, I can do score 1 plus score 2 plus score 3 in parentheses, because of order of operations, divided by 3, since there's 3 total scores. All right, so I think this checks out. And indeed, you can use parentheses and operators like plus in your code like this in C. Let me go ahead now and do make scores. No syntax errors, so that's good. Nothing missing there. And now let me do /scores and see what my test average is. All right, it's not great, but I think I still passed. And indeed, my average here is 59. Is it precisely 59, though? Well, let's see. Let's actually, instead of using an int, how about we go ahead and use something like a floating point value here. And let me go ahead and do this. So let me recompile my code, make scores. All right, I've got an issue. Let me zoom in on my terminal window. We've not seen this one necessarily before, but error on line 9. Format specifies type double, which is a lot of precision, but the argument has type int. So what does this mean? Well, it's showing me with these green squigglies that something's bad between the %f and this thing over here. Well, on the left, I'm implying a float, or a double for that matter. On the right, though, what data type are score 1, score 2, score 3? All right, so they're ints. So Clang does not like this. The compiler just doesn't like that I'm using ints on the right, but I want floats on the left. So there's going to be different ways of solving this. One way would be to just ignore the problem like I originally did and just go back to %i. Or, as an aside, %d is often an alternative to %i for a decimal number, but we use %i because it sounds like int. So %i is fine here too. But I don't want to just avoid the problem. I want to actually display a floating point value. So how can I fix this? Well, it turns out I can solve this in a few different ways. The simplest is just to make sure that at least one number on the right is a floating point value, like 3.0 instead of just 3. Now, I think Clang will be happier. Let me do make scores, enter. And indeed, it's OK. Why? As soon as you have at least one more precise data type on the right, it just treats everything at that point as floating point value so that the math works out. So /scores, enter. And now, there we go, right? Some of us might really want that third of a point. Our average was not 59. It's 59 1/3, as in this case here. All right, so we've solved that there. As an aside, though, there's one other technique to show here. If you didn't want to change it to 3.0, because that's a little weird, because there were literally 3 scores. It's not like that needs to have a decimal point. You could also explicitly convert the 3 to a float by saying in parentheses float. This is what's called typecasting. And this will just convert the thing right after it to that data type, if it's possible. So if I do this again, make scores, no errors now, /scores, and I get, in fact, the same result. There's a bit of a rounding issue here, but we know the rounding relates to the imprecision from last week. For now, let me just be happy with my 59.3 something. I'll take that for now. But this is, is close to a good enough correct answer for me now. But how do I think about now what's going on inside of the computer's memory? Well, let's consider. Here's that same grid of memory. Each box represents a byte. Where are score 1, score 2, and score 3 in my memory? Well, score 1, let me just propose, is at the top left. But it's taking up 4 boxes for 4 bytes. Score 2 probably ends up right next to it in memory, though this isn't always going to be the case. But I've chosen simple examples. 73 is next to it, also taking up 4 bytes. And then lastly, 33 is in score 3 down there underneath. Now, if we really look at the computer's memory, look at it with some kind of microscope or the like, there's actually 32 bits, 32 bits, 32 bits in each of those 4 groups of 4 bytes representing those values. But again, for today's purposes onwards, we don't really need to think again and again in binary. It's just indeed these decimal numbers being stored there. But I claim now this isn't the best design. Even if you had never programmed before CS50, what you're looking at here on the screen as an excerpt, in what sense is this perhaps bad design, even though it's a correct way of storing 3 test scores? What's kind of bad here? Yeah? Yeah, always do exactly what you did. Extrapolate to 4 scores, 5 scores, 50 scores. This can't be that well designed because now you're going to have 4 lines of code, 5 lines of code, 50 lines of code that are almost identical, except for this like arbitrary number that we're updating at the end of the variable. So indeed, there's probably going to be a better way, even though, at least in C, we haven't yet seen that technique. But the solution today onward is going to be something called an array. An array is a way of storing your data back to back to back in the computer's memory in such a way that you can access each individual member easily. Put another way, with an array, you can instead do something like this. Instead of saying int score 1, int score 2, int score 3, giving each a value, you can first tell the computer, please give me a variable called scores, plural, though you can call it anything you want, of size 3, each of which will be an integer. That is to say, this is how you declare an array in C that will have enough room to store 3 integers. Put another way, this is the technical way of telling the computer, please give me 12 bytes in total. 3 times 4 each for an int, so give me 12 bytes in total. And what the computer will do is guarantee that they're back to back to back in the computer's memory. And that'll be useful in just a moment. So let me go ahead and do something useful with this. Let me store 3 actual scores. Here's how I could now store those same numeric scores in this array. Syntax is a little different, but there's one variable called scores. But if you want to go to its first location, starting today, you use square brackets and go to location 0 first, which because things in C are 0 indexed, so to speak, you start counting at 0. The first int is at bracket 0. Second int is at bracket 1. Third int is at bracket 2. So it's not 1, 2, 3. It's literally 0, 1, 2. And this is not something you have control over. You must start at 0. So these lines now create an array of size 3, and then insert 1, 2, 3 values into that array. But the upside now is that you only have one name of the variable to remember. It's just called scores. Yes, you need to go into the array to get individual values. You need to index into it using those square brackets, but at least you don't have this hackish approach of declaring a separate variable for each and every one of these values. So let me go back to scores.c here, and let me propose that I do this. Let me just kind of use that same idea to do the following. Let me get rid of these 3 separate integers. Let me give myself an int scores array of size 3, and then scores bracket 0 will, as before, be 72. Scores bracket 1 will be 73. And scores bracket 2 will be 33. And let me get rid of the little dot there. All right, so now if I go ahead and run this again with make scores, enter. What did I do wrong here? I think I got a little too ahead of myself. Let me increase my terminal window. Let's focus on line 10 here first. Error, use of undeclared identifier score 1. What did I do here that was dumb? Yeah? Right, so I didn't declare score 1. I've got old code, right? So I just kind of honestly got ahead of myself here, not even intentionally. So let me go ahead and shrink my terminal window again. I need to finish my thought here. So let me clear my terminal, and let me change this now to be scores bracket 0 plus scores bracket 1 plus scores bracket 2. So it's a little more verbose because I've got these square brackets, so to speak. But I think now my code is consistent. So let me make scores now. It now compiles. /scores gives me indeed the same rough average with those same values. All right, so let me go ahead and maybe enhance this a little bit. It's a little silly to have to write a special program just to check your average of 3 test scores, like 72, 73, 33. Why don't I actually make the program dynamic and ask the human for that average, for those scores? So instead, let me do this. How about we get rid of the 72 and change this to getInt, and I'll just prompt the user for a score. Let me get rid of the 33 and change 73 and get this to be getInt score, quote unquote. And then lastly, get rid of the 33 and replace it with getInt, quote unquote, score. GetInt is a cs50 thing for now, so I need to include cs50.h as always. But I think now it's sort of a better program because now I can compile it once. I can even share it with my friends. And now any of us can average 3 scores on some class's test. They don't need to know the code or rewrite the code just to type in their scores. So make scores, worked, /scores. Now I can type anything I want. Maybe it's a 72, 73, 33. Still get the same answer. Or maybe I'm having a better semester, 100, 100, maybe 99. And now we get still a pretty high score there. But now it's dynamic. Now you don't need the source code. You don't need to recompile the program. It's just going to work again and again. But this too, let me propose that this code is correct if I want to get 3 scores from the user. But these highlighted lines now, 6 through 9, are they well designed, would you say? Yeah. Yeah, right? We can use a loop is the spoiler here. Why? I mean, my God, it's like the same code again and again and again. The only thing that's changing is the number. And it should have kind of had some code smell again, because if I keep typing the same thing again and again, like that's clearly an opportunity to better design something. So let me do this. Let me go ahead and still create my array of size 3. But let me use our old friend, the for loop, for int I equals 0. I less than 3, I plus plus, and then in here, let me do scores bracket. We haven't seen this before, but any intuition? Scores bracket I, because that will use whatever I is, be it 0 or 1 or 2 in iteration, and then I can get an int asking the user for score without having to repeat myself again and again. So hopefully, if I didn't make any typos, make scores. All good. /scores, 72, 73, 33, and we're back in business. But the code is arguably now better designed because now I haven't actually hard-coded the scores, and I haven't actually copied and pasted any of that code. Well, if we consider now what's going on inside of the computer's memory, it's pretty much the same in terms of the values. But instead of the variables being literally score 1, score 2, score 3, there's just one variable. It's an array called scores, but you can index into its 3 locations by using scores bracket 0 to get the first, scores bracket 1 to get the second, scores bracket 2 to get the third. But this is key. The memory is contiguous. It's only the screen is only so large, so it wraps around. But physically, digitally, the memory is contiguous, top to bottom, left to right. And that's important. Why? Because the brackets indicate 0, 1, 2, that each of these integers is just one integer away from the next. It can't be randomly down here all of a sudden. It's got to be back to back to back. All right, now equipped with that paradigm, what more could we actually do here? Well, it turns out it's worth knowing that it's possible in code to even pass arrays around as arguments. And let me just whip this program up somewhat quickly just so you've seen it before long. But let me go ahead and do this. Let me propose that I create a function that does this averaging for me. So I'm going to create a function called average that returns a float. And the arguments this thing is going to take, let's see, it's going to be the array. So it turns out if you want to take in an array of numbers, you can call it anything you want. This is how you tell C that a function takes not an integer, but an array of integers. And you don't have to call it array. I'm doing that just for the sake of discussion. It can be called x. It can be numbers. It can be anything else. I'm just calling it array to be super explicit as to what it is there. Now, how do I change my code down here? What I think I'm going to do for the moment is just this. I'm going to get rid of this code here, where I manually computed the average. And let me just call the average function here by passing in the whole array of scores. So this is just an example of abstraction. Like now I have a function called average. I don't care. I don't have to remember how it works once I implement it. And it just kind of tightens up my main code a little bit. But I do still have to implement this. So later in my file, let me repeat myself before. The only time it's OK in C to repeat yourself again and again by typing out again average and then int array, open bracket, but now not a semicolon. Now I have to implement this thing. And I can implement this in a bunch of different ways. But I don't know, in advance, I can't just do this. I can't just do array bracket 0 plus array bracket 1 plus array bracket 2, unless this program's only ever going to work on 3 numbers. So let me go ahead and do this. Let me first propose that there's a poor design here. In my main function, what value have I repeated twice? Among the highlighted lines, what jumps out at you as twice? Yeah, the length of the array is just 3. Now, it's not a huge deal that I type the number 3 on line 8, on line 9. But this is exactly the kind of like shortcut that's going to get you in trouble eventually. Why? Because eventually you or someone else is going to go in, make the array bigger or smaller. And you're not going to realize that magically that same number is in 2 places. And indeed, this is what a programmer would often call a magic number. A magic number is one that just kind of appears magically. And you're on the honor system to change it here if you change it here. And then you change it over here. Like, that's not going to end well if the onus is on the programmer to remember where they hard-coded, that is, wrote out 3 explicitly. So anytime you reuse a value like this, you know what? We should probably do what we did last week, which was to declare a variable, perhaps at the very top of my program, so it's super obvious what it is, called maybe n, and set that equal to 3. Better yet, what did I do last week to make sure that I can't screw up and accidentally change that value? Yeah, constant. And the keyword there was just const for short. And now I have a global variable, global in the sense that I can access it anywhere, that is called n. It's an int, and it's always going to be 3. And now I can improve my main function a little bit by just changing the 3's to n. So now if a colleague realizes, oh, wait a minute, there's 4 tests this year, you change n to 4, recompile the code, and it just works everywhere else. Except in my average function. Let me change it back to 3, just for consistency. This is not going to fly now to just sum up things like this, for instance, and then return this divided by 3. Why will this not work now, as I've defined it? Yeah. OK, I might be returning an integer value when I intend to return a float per this. But I think I'm OK, because I used that little trick where I made sure that at least one of the numbers in my arithmetic expression is, in fact, a floating point value. And just by adding the point 0, make sure that everything gets treated as a float. So I think that's OK. Oh, sorry, a little louder? Exactly. So left hand's not talking to the right hand here, in that my current implementation of average is still assuming that there's only going to be 3 tests or whatever. But wait a minute, I just went through the trouble of modifying this to be n generically. And if I change this to 4, I'm not going to be happy perhaps with my average, because now I'm going to ignore one of my test scores altogether. So let me change this back to 3. And unfortunately, if it's a variable now n, and therefore I have literally a variable number of scores, how do I take the average of a variable number of things? I mean, what's my building block there? Yeah? Yeah, why don't I use a loop that goes through the array and adds things up as you go? I mean, kind of like grade school. As you take the average on your calculator or paper pencil, you just keep adding the numbers together, and then you divide at the end by the total number of things. So how can I do this? Well, let me change my implementation of average to first declare a variable called sum or whatever, set it equal to 0. So this is like me on my piece of paper getting ready to count, or my calculator, of course, when you turn it on, typically defaults to 0. And now let me do for int I equals 0. I is less than a nope, I didn't do that. N, I is less than n, I plus plus. And now in here, let me go ahead and add to the current sum whatever is in the array's location I. And then down here, I think I can just return sum divided by 3.0 n. Perhaps here. And actually, I think I'm going to get, let's make sure it's a float. Let's use the typecasting trick just to make sure I don't accidentally shortchange someone and throw away everything after the decimal point. So it just escalated quickly, right? Like average just got a lot more involved. It's not just a single one line of code, but now it's dynamic. I initialize a variable called sum to 0. In this loop, I go through and just keep adding to sum, which is initially 0, whatever's in array bracket I, or specifically array bracket 0, array bracket 1, array bracket 2. That gives me a total sum that I return divided by the total number of things. Now, this I can tighten slightly. Recall that this is syntactic sugar for just adding things. I can't use plus plus, because that only literally adds 1. But I can use here plus equals. Questions on this implementation here? Really, the only takeaway, or the most important takeaway, is that this is the syntax for how you tell a function that it expects a whole array, not a single variable like an int or the like. You literally use square brackets, but you don't specify the length inside there. Yeah? What about the variable at the top? Good question. What do I have it defined as at the top, this variable n? It must be an integer if you're going to use it inside of an array's square brackets here. So this line 10, notice, no longer says 3. It says n. And so whatever n is, 3 or 4 or something else, that's how many integers I will get in that array. And it must be, by definition of an array, an integer that goes in those square brackets. And here's a common source of confusion. When you create the array, that is, declare it, you use square brackets like this, where you put the total number of elements you want. When you subsequently use the array, like I'm doing here, you don't mention int again, just like you don't mention int again and again once a variable exists. You use the square brackets still, but you don't use n. You use 0 or 1 or 2, or generically here, I. So when C was designed, they sometimes use the same syntax for two different ideas or contexts. Yeah? Good question. Do I have to include line 6? Short answer, yes, because of the reason we ran into last week. C, or Clang really, reads your code top to bottom, left to right. And so if the compiler sees some mention of this function average on line 16, but you haven't told the compiler that average exists, you're going to get an error on the screen. So the conventional way to do that is you just copy paste the first line of code from the function. It's so-called prototype or declaration. Yeah? Really good question and a perfect segue. Is there a library you can use if you don't know the size of the array? No. And so if any of you have programmed in Java or Python or other languages, you can actually just ask the array, like, how big is it? In C, you and I, the programmers, have to remember it. And so short answer, no. There's no function that will just automatically do this for us. And in fact, let me make a more subtle claim that it's fine to use global variables like this if they're really for configuration options. Why? It's just convenient to put them at the very top of the file because everyone, you, your colleagues, your TAs, are going to see them at the top of the code. But you really shouldn't be using them everywhere throughout your code. It'd be better if the average function itself were independent of that special variable. So by that, I mean this. You know what I should really do if I really want to be well designed? I should pass in the length of the array to the average function. I should give the average function a second argument. I'll call it length, for instance, but I could call it anything I want. And so rather than putting n all the way down here at the bottom of my file, let me just dynamically say length instead. And this is a subtlety, and no need to get too tripped up over this. But this now is just an example of how the same function can take not one but two arguments. But indeed in C, you must remember yourself what the length of an array is. You can't just ask the array via some syntax like you can, those of you who've programmed before in Java or Python. Yeah? Good question. Would it be better designed to write a function that computes the size? Short answer, can't do that in C. As soon as you pass an array into a function in C, you cannot figure out its size if it's a generic array like that of integers. There are special cases that you can do that, but in general, no. It's just not possible in C. And if that's some frustration, honestly, this is why more modern languages add that feature. Why? Because it was really annoying, as I'm alluding here, to not having that information. Now, just to make sure I didn't screw up anywhere, let me compile this final version of scores. Suspense, all good, /scores, 72, 73, 33, and we're still back in business. So this version's more complicated, and as always, we'll have this version on the course's website for reference. But the point really is that arrays not only can be used as containers to store multiple values, 3 or more in this case, you can also even pass them around as arguments. As such. All right, now besides that, let's simplify for just a moment and consider now the world of chars. If we've just got single bytes, where does this lead us, and how does this get us ultimately to strings to solve problems like readability and cryptography and the like? Well, here, for instance, are 3 lines of code out of context that simply store 3 chars. And you can already see where this is going. Having 3 variables called C1, C2, C3 is clearly going to end up being bad design because of all the silly redundancy here. But notice I'm using single quotes like last week because these are single chars. What does this look like in the computer's memory? Well, it looks a little something like this. If we clear out the old memory, C1, C2, C3 probably will end up here. Maybe not literally in the top left-hand corner. This is just an artist's rendition. But C1, C2, C3 will probably end up like that. Now, what's really there? It's really those same 3 numbers, 72, 73, 33. But how many bits does a byte have? Just 8. So if we were to look at the binary representation of these characters, it would only be 8 bits each. That's enough to store small numbers like 72, 73, 33. We're not dealing with Unicode and emoji and the like, but the point is the same. You don't have to use 4 bytes to store these numbers. You can use a different data type like chars, and underneath the hood, it's indeed going to use just single bytes for each. But this is sort of like this isn't really how we implement strings, right? When you wanted to say hi last week or this, we used double quotes, and we wrote all of the things together and used 1 variable, not 3, right? When I typed in David, I didn't have a variable for D, A, V, I, D. I had 1 variable called name that stored the whole thing. So in C, we keep talking about these things called strings. We'll see eventually that strings are not necessarily what they seem to be. But for now, the key thing about strings is that they're variable length, so to speak, right? They might be 3 characters, hi, or 5 characters, David, or anything smaller or larger. So how do we go about implementing strings if all we have at the end of the day is my memory? Well, here's an example of just creating declaring and defining a string called s. S because it's just a simple string, and quote unquote hi in double quotes. What does this look like in the computer's memory? Well, let's clear it again. And here now, because it's technically stored in 1 variable s, here's how I might draw it as an artist. It's 3 bytes in total, hi exclamation point, but there's no C1, C2, C3. It's just the whole thing is s. But it turns out that a string, fun fact, is really just what underneath the hood? Kind of leading up to this. What is a string if this is how it's laid out in memory? Literally, it's just an array of characters. And we didn't have to know about arrays last week to use strings. This is where, again, the training wheels are starting to come off. But a string is just an array of characters, hi exclamation point, for instance. So technically, an array, or a string called s, is really a variable called s that allows you to get at the first character with s bracket 0 if you want. S bracket 1, s bracket 2. You can literally get individual characters just by treating s as though it's an array, which it really is underneath the hood in this case. But there's a catch. How do you know where strings end? In the past, when I drew some integers on the screen, I claim they always take up 4 bytes. If I had drawn a long, it always takes up 8 bytes. If I had drawn a character, it always takes up 1 byte. But how many bytes does a string take up? Yeah, I mean, that's kind of the right answer. In this case, 3, it would seem. But if it's David, that's a good 5 characters. But where do we put the number 3? Where do you put the number 5, right? This is literally all that's into your computer. This is all our building blocks in front of us. So where does the 3 go? Where does the 5 go? Well, it turns out you can solve this in a couple of different ways. But the way humans decided to implement strings years ago is indeed an array. But they added 1 extra byte at the end of every such string array just to make clear with a so-called sentinel value that the string ends here. Why? So that if you have 2 strings in the computer's memory, like hi and bye, you know where the barrier is between like the exclamation point of one and the letter B in the next, right? You need some kind of delimiter. And so what really is underneath the hood is this. When you store a string in memory, when you type in a string as the user, if you type in 3 characters, it's going to use 3 plus 1 equals 4 bytes in total. If you type in David, it's going to use 5 plus 1 equals 6 bytes in total. Why? Because C automatically adds this special 0 at the end of the string. I've drawn it with \0 because this is how you represent 0 as a char, as a character. But this is literally just 0, as we'll soon see. So anytime there's a string in memory, it always takes up 1 more byte than you yourself as the programmer or human typed in. In fact, if we convert this again, just for discussion's sake, to those integers, what's literally stored in the computer's memory is going to be 72, 73, 33, and now a 0. And the computer, because of C and how it was invented, it's just smart enough to know that when you print out a string, it prints out every character until it sees a 0, and then it just stops printing. In particular, printf knows how this works. And this is why printf knows when to stop printing. Decimal numbers are not that enlightening. We'll generally write the characters like this. And again, \0 is just special symbology, like it's what the programmer types to make clear that you're not saying hi 0, you're saying hi, and then it's a special 0. Specifically, it is 8 0 bits that indicate that it's the end of the string. Technically, that \0, if you want to be fancy, it's called null, N-U-L. And it turns out you've seen this before, though we didn't call it out. Here's that same ASCII chart from the past couple of weeks. If I highlight this, what is decimal number 0 mapping to? NUL, which is just programmer speak for the special null character. All 0 bits, that means the string ends here. This all happens automatically for you. You do not need to create these null characters or these zeros. Any questions then on this implementation thus far? Any questions here? No? Well, let me do this. Let me go back to VS Code in a second, and let's actually corroborate this with some code. Let me go ahead and create a small program called hi.c. And how about we do this? Let me include standardIO.h. Let me type out int main void as always. And now let me do something simple and kind of bad, but char c1 equals quote unquote h in single quotes. Char c2 equals quote unquote I in single quotes. And lastly, char c3 equals exclamation point in single quotes. And now let me just print this out. I can't use %s because that is not a string. That's literally 3 chars because that's the design decision I made. But I could do this. %c, 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 which we haven't seen before, but %s is string, %i is int, %c is indeed char. So let me put a \n at the end for cleanliness, and now do c1, c2, c3. So this is like a char-based version of printing strings. So let me make hi, and then let me do /hi, and it looks like I used printf with %s. But I did things very manually by printing out each individual character. What's cool now, though, is that once you know that characters are just numbers and strings are just characters, you can kind of poke around. Let me change all 3 placeholders to %i instead. And this is totally fine, too. Let me rerun this. Make hi, actually, let me make one change just so we can see this. Let me add spaces just for aesthetic's sake. Let me do make hi, /hi, enter, and voila. Like now you can actually see the numbers that I claimed back in week 0 were in fact happening underneath the hood? Well, this is not how you would make strings. It'd be incredibly tedious to have 3 variables for 3-letter words, 5 variables for 5-letter words. We've been using, of course, strings since last week, so let's do that instead. String s equals quote unquote double quotes hi. For this, no, because of these training wheels, I need to include the cs50 library, but we'll come back to that in the coming weeks. But for now, I'm going to go ahead and create a string s called quote unquote hi. And now I'm going to change this to be my familiar %s, and now just print out s itself. This, of course, is the same thing as last week. /hi gives me the exact same thing. But now we're dealing, of course, with strings. But how can we see a little beyond that? Well, how about this? Let's poke around further with today's primitives. Even though s is a string, I could technically print out its first character with %c by doing s bracket 0. I could technically print out its second character with %c by doing s bracket 1. I could print out its third character with %c and printing out s bracket 2. So again, this just derives logically from my understanding now of that strings are arrays, as you note. Let me do make hi. /hi, and no visual change, but I'm just kind of now tinkering around. And in fact, if you're really curious, let me do this. Let me change these back to I, back to I, back to I, and let me add a fourth one, because if I'm really curious now, let's see what's at s bracket 3. This is the 4th byte, and even though the string itself is hi, I think we can corroborate this whole null thing. Make hi, /hi, enter, and there it is. You could have done this last week if you really wanted to geek out on strings, but like for now, it's just revealing what's going on underneath the hood. Questions then on what these strings are? Yeah? Why do we need the bracket? Why do you not need brackets? Good question. Why do I not need brackets on line 6? Because s is a string. We'll see in a couple of weeks that s is essentially implemented underneath the hood, indeed, as an array. But that happens automatically for you. You can treat s as just a variable name without square brackets. You will use square brackets when you have arrays of ints, or you manually create arrays of chars, or doubles, or floats, or anything else. But strings are special. Why? I mean, every program you write seems to use strings, text in some form. We're humans. We like text, not just numbers and such. So this is just treated a little specially in C and many other languages as well. All right, other questions on this here? No, let's add then one other string to the mix. So instead of just saying hi, why don't we consider a version of the program that says both hi and bye? And I claim now that that \0, that null character, is going to be ever more important now if we've got 2 strings in memory so that C knows how to distinguish one from the other. So let me go ahead and just get rid of these 2 lines for the moment. Let me recreate string s equals quote unquote double quotes hi. Let me give myself another one. And because I'm just playing around, I'll choose very short variable names. String t equals quote unquote bye exclamation point. And then let me just print them both out. Let me go ahead and print out %s \n comma s, and then printf %s \n, and then t. So very simple demonstration of just these 2 variables, make hi, /hi, and of course it prints out 2 lines, one after the other. What's actually going on underneath the hood? Well, let's go back to the computer's memory. Hi, I think, is going to be, I claim, pretty much the same. So s, I'll claim, is in the top left, followed by the \0. And that's important now because bye probably is going to end up there. And visually it wraps just by nature of how I've drawn this grid of bytes, but it's contiguous. B, Y, E, exclamation point, null, aka \0. This is now helpful to printf because now printf knows where one begins and ends by way of that special null character. But we can poke around now too. What else can I do here? How about this? How about I go into my code here, back to VS Code, and let me go ahead and say something like, well, if I've got 2 of these strings, well, let's put them in an array. Let's kind of do this sort of arrays in arrays, sort of Inception style here. So string words, bracket 2. So give me an array of 2 strings is what I'm saying here in code, even though we've not done it with strings yet. We only did it with ints. And now let me do this. The first word, aka words bracket 0, will equal, as before, hi. And now words bracket 1 will equal, quote unquote, bye. Bytes. So bye And now I've done the exact same thing. But again, I'm just avoiding having S, T, Q, R, and like all these different variables in my code. I just now am treating them as one single array of strings. How do I change my code down here? Well, if I want to print the first word, I do words bracket 0. And if I want to print the second word, I do words bracket 1. This is not a useful exercise at the moment, because I'm just making my code more complicated. But again, it allows us to poke around and see what's going on, because there's that hi and bye. But watch this. If I really want to be cool, I can do this. Let's print out %c, 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 \n. And then here, %c, 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 %c. So 4 of those. And now, here's where things get interesting. Words is an array of strings. But again, if I may, what's a string? An array of characters. So just use the same logic. If words is an array of strings, you get at the first string with words bracket 0. How do you get at the first character in the first string? Bracket 0. Words bracket 0, bracket 1. And lastly, words bracket 0, bracket 2. And now down here, words bracket 1, but the first character is there. Words bracket 1, the second character is here. Words bracket 1, the third character's here. Whoops. Third character's here, and words bracket 1, the fourth character is here. Like, this is not how people program. This is only for demonstration's sake. My God, it's so tedious and verbose already. But if I make hi now, /hi, now I'm like manually reinventing %s if I forgot it existed using %c alone. But you can indeed manipulate arrays in this way. But because strings are arrays of characters, you can manipulate strings in this way too. Any question now on this syntax? Any questions here? No? No? All right. Well, let's go ahead and propose that we solve a couple of other problems we might not have as before. But first, a quick visual of what's been going on underneath the hood here. If here again is where we left off on the screen, hi and bye back to back, here is really how I just treated these things. S bracket 0, 1, 2, 3, and then T 0, 1, 2, 3, 4. But really, once I put them in an array, the picture becomes this. Words bracket 0 is the whole hi. Words bracket 1 is the whole bye. But if I really get into the weeds and start indexing into individual characters in those strings, all I'm using is new syntax in order to represent these same values here. Questions then on these representations before we forge ahead? No? Yeah. Does the new line character, say that once more? Really good question. Does the new line character take up any space? It does when, so far as printf is concerned, but I'm not storing the \n in my strings. Printf is being manually handed that thing instead. All right, so let's go ahead then and consider how we might solve some problems that have arisen now with these strings as follows here. Suppose let's do this. Let me go back to VS Code here, and let me go ahead and open up a new file called, how about length.c. And let's consider for a moment how I might actually figure out what the length of a string is, which is distinct from the length of an array. I claimed earlier you cannot figure out dynamically what the length of an array is, but I can figure out the length of a string specifically because of this implementation detail of that null character. So let me go ahead and do this. Let me include cs50.h in this second program here. Let me include standardio.h as before. And let me do this. Int main void. And in the first thing I'll do is just get a string from the user. I'll ask the user, as always, for their name. So I'll call getString and say, what's your name, question mark, as always. And then down here, if I want to figure out the length of this string and print the name, print the length out on the screen, well, I can kind of do this similar in spirit to the average, where I'm accumulating something. Let me go ahead and initialize n to 0. Let me give myself it's not a for loop because I don't know in advance how long it is. But what if I do this? While the value at name bracket n does not equal single quote \0. Crazy syntax at the moment, but it's just the culmination of these various building blocks. Let me just finish the thought here. N++. And then down here, let's just print out with printf and %i that value of n. So I claim this is going to show me the length of any string I type in, whether it's hi or bye or David or anything else. I initialize a variable to 0. And that's good because that's where you start counting in general. While name bracket 0 does not equal \0. What is this saying? Well, if name is the string the user typed in, and name is just an array, as you noted, then name bracket 0 is going to be the first character. And I'm asking the question, well, does the first character not equal \0? And if I type in David, D, it's not. So I keep going, and I add 1 to n. Then I'm going to check name bracket 1. Well, if I typed in David, name bracket 1 is going to be A. A does not equal \0, and so it's going to go again and again and again. But 5 steps in total later, it's going to get to the byte after DAVID, realize, wait a minute, that is a \n. The loop finishes, and I print out the total length. Arrays in general do not have this null character. However, strings do. Again, strings are special versus all of the other data types we've talked about thus far. But how could I, for instance, do this differently? Well, let's actually factor this out as a function, as I've commonly done. But rather than implement it myself, you know what? It turns out what's nice about strings being so common, there are many other people who have solved these problems before. And in fact, there's a whole string library in C. It is used by way of a header file called string.h. And what string.h is a library of string-related functions. In fact, you can see in cs50's manual pages for C, the string.h functions, at least those that we recommend as most useful. And in particular, if you poke around there, you'll see that there's a function called strlen. Means string length. It was named very succinctly just because it's a little easier to type than string length. But strlen tells you the length of a string. So how might I use this in my code here? Well, it turns out I can simplify this quite a bit. Let me get rid of my loop, get rid of my, my counting manually, and do something like this. Int n equals strlen of the human's name, And now I'll just use printf as before with %i\n and output the value of n. But there's a bug at the moment. What have I forgotten to do? Yeah, I have to include the header file at the top of the screen. So at the top of the code. So let me also include string.h at the top of my file so that C knows that, in fact, strlen exists. Let me go ahead and make length as before, /length. Or actually, really for the first time, what's your name? DAVID. And hopefully, I'm going to see, in fact, 5. By contrast, if I run it again and type in hi exclamation point, now I see 3. So strlen is just one of the functions in that library, and there's so many more. In fact, yet another library that might be useful moving forward is this one, ctype, which relates to C data types and lots of functions therein that can be useful. For instance, if you review its documentation in the manual pages online, you'll see that there are functions via which we can solve problems like this. Let me go ahead and propose here. Let me see. Let's do example here involving how about checking if something is uppercase or lowercase and converting it to uppercase only. Let me go back to VS Code and code a program called uppercase.c. In this file, I'm going to start by including now, as always, cs50.h. I'm going to include standardIO.h. And I'm going to add one other to the mix, which is string.h now too. So I can access the length of things as needed. Int main void comes next. And then within my main function, I'm going to go ahead and declare a string called s. I'm going to call getString as before. And I'm going to go ahead and just ask the user for a string called before. I want to do a before and after. Whatever the user types in is before, but I want to force everything to uppercase thereafter. Let me now, in this loop here, do this. Let me printf, quote unquote, after, just so we can see this on the screen. And let me do for int I gets 0. I is less than strlen of s, I++. What am I about to do? I'm about to iterate over every character in the string from left to right, from 0 on up to, but not through the length of s. And how do I check if something is lowercase so that I can actually force it to uppercase? Well, it turns out I could do this literally. If the character in s at location I is greater than or equal to capital A, ampersand, which means and instead of or, which we saw in the past, s bracket I is less than or equal to little z, that means logically in English that this is indeed lowercase. How do I now convert it to uppercase, this character? Well, I could just literally print out the same character, but that would not be the answer here, because that's not changing the value. But what could I do instead? Well, let me actually pull up here real fast the ASCII chart as before, and let's see if we can't glean some insight. If I pull up the same ASCII chart, and suppose the human has typed in a lowercase a, that's 97. What letter? I want to convert it to uppercase A. So what number do I want to convert the 97 to per week 0? So 65. We keep coming back to that one. What if the user types in lowercase b? I want to change the 98 value to 66 and so forth. And any quick math, how far apart are those? So it's always 32. Like uppercase to lowercase is always, wonderfully, good design, 32 away, one from the other. So what does this mean? Well, I think we saw earlier that underneath the hood, a char is just a number. You can certainly do arithmetic on it. And here again, if you understand these lower level primitives, what if I do this? Whatever s bracket I is, if I know on line 13 that it's lowercase, do I want to add or subtract 32? So I want to subtract because I want to go from like 97 to 65 or 98 to 66. So indeed, if you do some quick math, that gives you 32. So it suffices to just treat chars as numbers, subtract the 32, and printing it with %c, I think will just convert lowercase to uppercase. If you now fast forward to like the real world, Microsoft Word or Google Docs, if you've ever chosen the menu option that forces things to uppercase or lowercase on occasion, literally that's what Microsoft and Google have done. They iterate over every character in the document, check if it's lowercase, and if so, they subtract 32 from it and show you the new value. What if, though, it is not a lowercase letter? I think I can keep it easy and just print out the current letter unchanged if my goal is to simply force things to all uppercase, and that letter then would be s bracket I. So let me go ahead now and make uppercase. Hopefully no errors. /uppercase. And I'll now type in David with an uppercase D, but lowercase everything else. But now the after version is David. An aesthetic bug. Notice here I forgot to include, just for prettiness' sake, a \n at the end. No problem. I'll add that. Let me fix my mistake. Make uppercase. /uppercase enter. DAVID enter. And voila. And I deliberately added another space after the after just so that they would line up pretty, even though before and after have different numbers of letters. Questions then on this implementation of forcing something to uppercase, which in and of itself is not all that enlightening, but is representative now of how you can leverage these low-level primitives. Question? No? All right. Well, this honestly is tedious. My God, like does Microsoft, Google, everyone, you have to literally write out this code just to do something simple? Well, no. That's again why we have things like libraries. And increasingly now for problem sets, projects, and beyond, well, you just use libraries more often off the shelf so as to solve problems that surely other people have had before you. So how can I now use this library, ctype.h? Well, let me go back into my code. Let me include this among my header files here. I tend, just so I can skim things easily, I tend to alphabetize my headers, but that's not strictly necessary. But it allows me at a glance to realize, did I or did I not include something I need? Now let me go ahead and do this. It turns out if you read the documentation for the ctype library, there's a function wonderfully called if is lower that takes in a character as its argument, essentially, so s bracket I. And if that returns true, a Boolean value, if you will, well, I'm going to force it to lowercase. But I don't have to do this math anymore. Turns out in the ctype library, there's also a function called toUpper that takes a character as input, like s bracket I, and it just does the math for you so that you can abstract away the 32 thing and just know that someone else has solved that problem for you. Otherwise, I can leave my code unchanged down below because I'm not changing anything else. So if I do make uppercase now, and then /uppercase, DAVID with just a capital D, and now it still works. But if you read the documentation further, it turns out that toUpper is smart. If you pass in a character to toUpper that's lowercase, it obviously converts it to uppercase by doing that math. But if you pass in a character to toUpper that's already uppercase, the documentation you would see tells you that it leaves it unchanged. So I can tighten all of this up. I can get rid of the whole else. I can get rid of the whole if, and arguably now implement a program that's just as correct, but better designed. Why? Fewer lines of code, easier to read, lower probability of mistakes. Assuming the library is correct, it just makes it easier and faster for me now to write code. So if I now do one last time, make uppercase, enter, /uppercase, and type in my name, still working. But now notice we've whittled this down to far fewer lines of code, albeit using now this additional library. Questions then on how we did this? All right, a few final building blocks for the day. So we started by talking about those command line arguments that Clang uses, whereby anything after the command that you type at a prompt, be it make or Clang or even CD in Linux, any word thereafter or something cryptic like -o is a command line argument. It's an input to the command. It's different from a function argument because a function argument, of course, is an input to a function. But it's the same idea. It's just different syntax after the $sign at the prompt. Well, it turns out that command line arguments are something you can now use in your own programs by accessing words after the prompt. And let me propose that we invent this as follows. Let me propose that we switch back to VS Code here. And I'll open a new file here called greet.c. So in greet.c is going to be a program that very simply greets the user. Had we written this last week, we would have done this. Include cs50.h, and then include standardIO.h, and then int main void. And then we might do something simple like string name equals get string, quote unquote, what's your name question mark. And then we would have printed out, as always, hello, comma, %s, and then plugging in that name. So this is the same program we've implemented many times just to make sure it works. Although, nope, that's not quite the same program. Semicolon's in the wrong place. This now is the same program. So make greet /greet, and I'll type in my own name, hello, David. So we're back there. Now, what's arguably a little annoying about this program, if I type in something else like Carter, enter, I have to run the program, wait for the prompt, type in my name, hit enter. And that's fine. But imagine if every program worked like this, like make. Suppose you could only type make. Then you wait for a prompt. Then you type the name of the program you want to make. Then you hit enter. Or worse, in Linux, when you have to change directories, as you might have for problem set 1, what if you had to type cd, enter? Now type the name of the folder you want to change into, enter. I mean, it just slows life down. And so it just gets annoying quickly. So command line arguments just let you express your whole thought all at once. So how can I do this? Well, if I want to express the notion of command line arguments in my code, I could do something like this. I could, for the very first time, go up and get rid of this void, which as of today means this program takes no command line arguments. And I can change it to exactly this. Int argc string argv with brackets. Now, it's cryptic, admittedly, and let me zoom in. But I think we can perhaps infer now what's going on. If main now does not have void as its input, which means it takes no arguments, surely the spoiler here is that now main will take command line arguments somehow. Any guesses as to what argv is or will be? What might this represent? It's an array of strings, right, by way of the syntax. Yeah? Exactly. It will be all of the characters, or really all of the words that you type at the prompt. Argc as an int, any guess? Argument count is what it generally stands for, though technically you could call these things anything. But this is the convention. Because I claimed earlier that arrays don't keep track of their own length, if you want to know how many words the human typed at the prompt after your program's name, you have to be told not just the array of the words, but the length of that array. The strings you can figure out the length of using strlen, but you can't figure out the length of the array of strings, the collection of words that the human typed in. So how can I now use this? Well, let me go ahead and do this. Let me go ahead and change this program now just to be printf, quote unquote, hello, comma, %s \n, then argv bracket 1. So this is not the best version of my code yet, but it's my first. Make greet, and now let me do /greet David all at once. Enter, hello David. Now let me run it again. /greet Carter, enter, hello Carter. You know, it's a marginal improvement, but I don't have to wait for getString to prompt me to hit enter. It's just speeding things up, you know, twice as fast, one less command to type in. But I deliberately did bracket 1, but what's the beginning of argv? It would be bracket 0. Well, what's that? This is sometimes useful, though for now it's not. Suppose I recompile my code and run this program now, greet David. Anyone want to guess what's in argv0? Say again? Greet. Enter. Hello./greet. So if you want, sort of Inception style, your program to figure out what its own name is, or at least how it was executed at the command line, at the terminal, you can look at argv0. In general, probably not that useful. Probably better to start looking at bracket 1, which was the first word after the program name. And if there were more, I could do this. How about argv bracket 2? Let me add in a second %s. Let me recompile greet. Let me do /greet David Malin, enter. And that too now works, taking in 2 words at the prompt. If I really want to be smart at this now, I could do something like this, though. How about if the count of arguments, aka argc, equals 2, then assume that the human typed in only their first name, and do printf hello, comma %s, \n, and then argv bracket 1. Else, if the human did not provide exactly 2 arguments, the name of the program and their own name, let's just print out a default value, lest they forgot their name or they typed in 2 names or 3 names. Let's just do hello, comma, world as a default, and we'll just ignore what the human typed in. If I recompile this, make greet, I can do /greet and David again, enter. Oops. Sorry, what am I missing? Yeah, so newbie mistake. Else. All right, make greet again, /greet David, enter. There's my hello David. But if I omit my name, I just get the generic, like a default value. And if I get a little curious and I type in both names, then I get ignored too. Why? Because I just haven't built in support for argc of 3. I could do anything I want, but now we have access to these kinds of building blocks. All right, what else might I do here? Well, it turns out there might be some final features for us to now execute. Notice, though, that in C, despite what you might see in books or online tutorials, nowadays, the 2 official formats for defining a main function are either this, which we've been using now for 2+ weeks, or now this, whereby you change the void to int argc, and then for now, string argv, and then empty brackets. And we'll see that this too is a simplification, some training wheels, if you will. But for now, those are the 2 forms. Even though you will see in online tutorials and even books, some people use main in different ways. These are the 2 now to keep in mind. And I'll note that these command line arguments are kind of all over the place. Didn't probably expect to see this word on the screen here. And what does it mean? Well, it turns out that for decades, there's actually this program that comes with Linux systems in particular called cowsay. Why? Probably because someone had too much free time once and decided to write a program that creates ASCII art out of a cow saying something textually on the screen. But you use cowsay, just for fun, by way of command line arguments. So for instance, let me propose that I go back to VS Code here. Not because I want to write any code, but I just want to use my terminal window. And let me maximize my terminal window here. And let me go ahead and type in something like, how about cowsay space moo. So cowsay is not a program I wrote. It's been around for decades, but we installed it in VS Code for you in the cloud. It takes at least 1 command line argument. What do you want the cow to say? I can say cowsay moo and hit enter. And voila, there's my ASCII art of a cow saying moo on the screen. It can say multiple words. So I can say hello world, enter. And now it says hello world. So this is just an example of a silly program that uses command line arguments, but it takes others too. Just like Clang used this convention of hyphens to change the output of the program, dash something is just a super common convention with command line arguments when you want a very terse notation for some option, like output. In cowsay, I read the documentation, and it turns out there's a -f command line argument that allows you to change the appearance of the cow, if you will. So if I do cowsay -f duck, and then some other word like quack, it's no longer a cow. That command line argument turns it into a tiny, adorable duck instead. And then lastly, just for fun, because I spent way too much time playing with command line arguments, cow say -f dragon, and then how about like rar, enter. You can even get this on the screen here. So this, too, is just an example of what you can do with these command line arguments now that we have this building block. And there's one final thing we can now do with code. There's one last feature today that we'll introduce before we now connect all of these dots to readability and encryption by talking lastly about something called exit status. It turns out that whenever your main function exits, it returns a secret integer that you can figure out as the programmer or an advanced user what it was. And these exit statuses are typically used to indicate errors. So for instance, over the past couple of years, if you've used Zoom and you ever got some kind of error, you might have seen a screen like this. It's usually not that helpful. Maybe tells you to click report problem or contact support. But very often in our human world on Macs, PCs, and phones, you see cryptic error codes, like literally numbers that probably only Zoom knows, or Microsoft, or Google, or whatever company wrote the software you're using. But that number corresponds to a specific error that some human somewhere knows might very well happen. These are used similarly, although under a different name that we'll talk about later in the term, on the web as well. Have you ever seen this, maybe not character, but number? So 404 means what? So error, yes, but really not found. So why? I mean, this is the most arcane thing, and we'll talk in a few weeks about like what this and other numbers mean. But numbers are all around us in technology, and they very often mean something to the technical people who wrote the software, less so to humans like you and me. Why so many of us recognize 404 is kind of weird, that like that's been around long enough that we all know it, but it really is just a special number that represents an error of some sort. So it turns out the last thing we'll reveal today about what we've been taking for granted for 2 weeks is what the int is in main. We've seen just a moment ago that the thing in the parentheses, which up until now has been void, which means no command line arguments, now int argc string argv brackets just means yes, command line arguments. And we've seen how to access them. So the last piece of the puzzle, honestly, of all the cryptic syntax the past 2 weeks, is just what int means. And in fact, you don't need to use command line arguments to have this discussion. So let me revert to the simpler form. Int is always there for main, and it indicates that main will always return an integer, even though you and I have never done so explicitly. Usually, main returns 0 by default. But it would be weird if you saw an error message saying 0. So 0 is just hidden. You would never see it on the screen. But it's happening automatically by way of how C is designed. So let me write one final program here. I'll call it, for instance, status.c to show you these exit statuses. Code of status.c. And then up here, let me do something simple like include cs50.h, then include standardio.h, and then int main. Let's use a command line argument. Int argc string argv. So that's copy paste. But now let's do this. If argc does not equal 2, why don't we do something like this? Let's not just default to hello world like last time. Let's yell at the user. So let's say something like printf missing command line argument, so that they know they screwed up and they need to run the program again correctly. Else, let's go ahead and say print out, as before, hello, comma, %s, and then plug in argv bracket 1, so the human's name from the prompt. Now at this point, let me go ahead and run status, /status, and I'll type nothing first. I get yelled at. This time I'll type it again, /status David, and it works properly. But now let me show you a somewhat secret cryptic command. You can type this at your prompt, and it's just a coincidence that there's another $. Echo $? Totally arcane, but it allows you to see what exit status your program has ended with. So let me run this again the wrong way. /status. OK, I get the error message. What was secretly returned? I can't see it. There's obviously no error screen. But by typing echo $? I can see that, oh, my program automatically, by default, returns 0. However, if I run it again correctly, /status David, enter, this is the correct version. But if I run echo question mark status again, it's still entered with 0. And long story short, this is just a missed opportunity. When something goes wrong, why don't I return a value other than 0? 0 by default means success, and it's always there automatically. But you can control this. I can go into my code here and return 1 or 2 or 3, or what was it in Zoom? I could even return 1132 just because Zoom did that too. Else, if something works fine, I can return 0 by default. And honestly, if I omit the return 0, again, 0 automatically is returned. So let me go ahead and though be explicit, just so I know what's going on. Make status again, /status, and let's do this correctly with David. Enter, hello David, echo question mark, echo $? 0. So all is well. But now if I do /status and nothing, or multiple things, but not just David, enter, I get the error message. But now if I do echo $? Oh, damn it. I shouldn't have chosen 1132. Let me cheat. Pretend that didn't happen. I'll explain sometime. /status without anything, enter. We indeed see the error message, echo $? Voila, there now is the 1. So I used too big of a number. This is, I'm going to surmise it's only using 8 bits, even though we called it an int, which means we were overflowing the 8 bits. And that's why 1132 suddenly became much smaller. But I'll double check that to be sure. This is why I shouldn't go off script. So what does this now mean? This is, in the graphical world, we would just show something like this on the screen, which is a little more informative to the user. But even in the Linux world, where you don't have a GUI necessarily, even for the programs we've written, you can check these exit statuses. And in fact, more comfortable, more advanced programmers, when they write code that calls programs, be it cow, say, or anything else, you can in code check what the exit status is of a program and then decide, did my program work or did it not? So if you go on to do things in data science or in general analyzing data, writing scripts, writing programs to analyze data, it's just very useful to be able to check programmatically with a command like echo $? Weird as it looks, did my program succeed or did it not, even without seeing something user-friendly or graphical or textual on the screen. And now let's connect the final dots before we adjourn for some fruit snacks. Cryptography, namely one of the applications this week via which you'll be able to send, if you will, secret messages, and better yet, decrypt secret messages. This will be in addition to perhaps analyzing the readability of text using heuristics, like we identified at the start of class 2. So cryptography is just the art, the science of encrypting information, scrambling information, so that if you have a secret message to send in so-called plain text, you can run it through some algorithm and turn it into what's called ciphertext, thereby encrypting it. And only someone who knows what algorithm you've used and what input you've used to the algorithm, theoretically, can decrypt that process and convert it back to the original message. So if we use our mental model from last week, here is a problem. Here is an input and output. The goal, I claim here, is to take some plain text, like the message you want to send. Think back to grade school. If you ever passed a note to a friend or to your crush saying, I love you, it's a little awkward if the teacher or someone else intercepts the paper and in English it just says, I love you, or whatever it is. It'd be nice if you had at least encrypted it in some way. But the other person needs to know what algorithm you used and what inputs you used to that algorithm so that ultimately they can decode the so-called ciphertext, which is the output. So what goes inside of the box today? Well, an algorithm, as it relates to cryptography, is called a cipher. And a cipher is a fancy name for an algorithm that encrypts text, from plain text to ciphertext. The catch is, there needs to be not just the algorithm, there needs to be an input to it. And so, for instance, you might draw the picture like this for the first time today. And we've seen this in code. You can give multiple inputs or arguments to functions. So in this black box, can you imagine passing in the message you want to send and then some secret? So for instance, suppose that the simplest thing I could think of as a kid was, instead of sending the letter A, why don't I write the letter B? Instead of the letter B, why don't I write the letter C? So I can kind of shift the English alphabet by one space. So A becomes B, B becomes C, ... Z becomes A. You can wrap around at the end. And let's assume no punctuation in this part of the story. So that's a very simple algorithm. Add a value to each letter and send the value as the ciphertext. And now the teacher, the classmate, they have to know that you use not only this rotational algorithm, also known as a Caesar cipher, they also need to know what number you use. Did you add 1 to every letter, 2 to every letter, 25 to every letter? Now, if they're super smart, and probably not the young age in this story, they could also just try all possibilities. And that would be an attack on the algorithm. This is not a sophisticated algorithm. But it's enough to send a message in class. So if the 2 inputs now are hi as the plain text message, and 1 as the so-called key, the secret number that only you and the other person know, you might be able to encrypt a message from one way to the other. And so in this case, for instance, hi would become IJ! Exclamation point. In this version of the algorithm, we're not going to bother with numbers or punctuation. We'll only operate on A through Z, be it uppercase or lowercase. So now if you were to receive a slip of paper in class with IJ on it, you, the recipient, would know what it is so long as you know that the sender used 1, because you just reverse the algorithm and you subtract 1 instead. The teacher, they probably don't know what this means, and they're not going to spend time hacking the message, so it just looks scrambled to them. And that's what we get from encryption. Someone who intercepts it, be it in class or in the real world, on the internet or anywhere else, can't actually figure out, ideally, what it is you have sent. The opposite, of course, is indeed called decryption, but the process is the same. We now pass in -1. And so how about this? Why don't we end with a demonstration here? UYJTXBTDT50. There's a bit of a tell there. If we pass that in and do -1, well, how do we get out the plain text originally? Well, if this is the ciphertext and we subtract 1 from each letter, I think U becomes T, I becomes H, J becomes I, T becomes S, X becomes W, B becomes A, T becomes S, D becomes C, T becomes S. And this was indeed CS50. Have a duck on your way out and some snacks in the lobby.